All right, chemistry students, we are looking at another chapter in our course, and we have already talked about matter, and then we talked about scientific measurements. We are going to dive into one of the most important topics because it's going to be something that we're going to talk about for the rest of the class, the rest of this course, and that is the atom. And the atom is the basic building blocks of the matter that we see all around us. So let's dive into this. We have in chapter 3 the topic of the atom, and it is called the building blocks of matter. So an important topic here, obviously, if this is the building block of matter, obviously we're going to build the rest of the course upon this. Okay? We're going to look in section 1 at the atom itself, and we'll look at the structure of the atom, and then we'll talk about, well, how do we count these atoms? Because they're so small. Even in a small container, there's going to be an astronomical number of atoms. So how do we kind of put them in a package? Okay? If you would, pause the video, and in your notes, as we do with all of these videos, you're going to need to take notes on this and make sure you submit it. Just answer these two questions to the best of your ability. So pause the video right now and answer these two questions, and then come back. All right, in this first section for chapter 3, we're going to look at the atom and talk a little bit about just the concept of it and how it applies then to the structure of compounds and some of the laws that are behind that. Okay? We're going to look at 3 basic laws that describe how matter behaves in chemical reactions. And again, it's all based upon the idea of this atom. Here's the first one. It is called the law of conservation of mass. Basically, what it's saying is an atom, since it's the basic building block of matter, you're not going to be able to destroy or create new ones during a chemical reaction. You may change the bonding, or what it's bonded to. An atom it might be bonded to something else. You may pull apart bonds and form new bonds, but since the atom is not going to be destroyed or new ones created, then since they have mass, we know that the mass before the reaction and the mass after the reaction has to be the same. So what it says is mass, you could just as easily say atoms here. Okay? Atoms, since they have mass, they're neither created nor destroyed during ordinary chemical reactions or physical changes. Now we say ordinary because scientists are getting more and more sophisticated, and they're smashing things together and trying to create new stuff. But during ordinary chemical reactions, mass is not going to be created or destroyed. The mass before the reaction has to equal the total mass after. And I say total mass here because you would add up all the masses of the reactants, and that would equal all the masses of the products. Okay? All right, the other one is the law of definite proportions. Now you should know a proportion is like a ratio. This is basically saying is a compound. This is just a single compound now. A compound contains the same elements in exactly the same proportions regardless of sample size or source of the compound. What that means is if you have water, which is H2O, it doesn't matter how much water you have, a small glass or gallons and gallons or a tank or a lake or whatever, the ratio, the proportion in which hydrogen and oxygen combine to make water is always going to be 2 parts hydrogen to 1 part oxygen. 2 atoms of hydrogen are going to be bonded to 1 atom of oxygen. That is always the case. They're always going to be bonded together in a 2 to 1 ratio. Always, always the case. Okay? So you should have this first law written down. You should have the second law written down. And again, you can put them in your own words and even use my example here. The third law is talking about multiple proportions. So that means we're going to have more than just one compound. Again, this law up here is just looking at one compound, like H2O. Hydrogen, oxygen are a 2-to-1 ratio. Now we're talking about multiple compounds that have the same elements. If two or more compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is a ratio of small whole numbers. I know that sounds very complicated, but basically what we're saying is if you've got carbon monoxide, carbon and oxygen can bond to form just carbon monoxide, that's just carbon and oxygen, one atom of each, or carbon dioxide. You can form carbon dioxide as well. So we have the same two elements forming different compounds. Okay? Well, that says that basically that the second element combined with a certain mass of the first element is a ratio of small whole numbers. Let me give you an example down here. They give us a nice example right here. All right, with our carbon monoxide and carbon dioxide. So carbon monoxide can be formed, and in carbon monoxide, there's 1 gram of carbon. Carbon monoxide is just carbon and oxygen bonded together. 1 gram of carbon for every 1.33 grams of oxygen. So you have a 1 to 1.33 ratio of the masses. All right, in carbon dioxide, that's CO2, there is a 1, you just have 1 carbon again, but this time to 2.66. You have twice as much oxygen, carbon dioxide. So the ratio between the oxygens here, you'll notice, is what? It is a 1 to 2 ratio. 1 to 2 ratio. In this one, you have twice as much oxygen. They're going to be multiples of whatever the single mass is, the mass here is of the oxygen when it's just CO. Okay? That's all it's saying. And that is for multiple proportions. All right. Along comes an English school teacher named John Dalton, and he is very, very curious, as any good scientist would be, about this idea of an atom. And he proposed some ideas, or what eventually became laws, and some of these still hold true, some of them may not, but he reasoned that elements were composed of atoms, and that only whole number of atoms can combine to form compounds, kind of like what we said before with H2O. It's always going to be 2 atoms of hydrogen to 1 atom of oxygen. Here are 5 ideas that he came up with, and you must know these for Dalton's atomic theory. 1, all matter is composed of extremely small particles called atoms. That is still true. Okay, way back in 1808, and this is still true today. We have not disproven that. Number 2 says atoms of a given element are identical in size, mass, and other properties. So that means hydrogen, the hydrogen atoms are unique to hydrogen. They have a certain mass, size, and they have certain properties. As well as oxygen or any other element, their atoms are going to be unique to that particular element. Okay, and that is still true. You need to know that. Number 3, atoms cannot be subdivided, created, or destroyed. Well, this is true. They can't be created. We can't create atoms necessarily, although, as I mentioned before, scientists are colliding things together in order to try to make new elements and thus new atoms, so that's not entirely true. Destroyed, again, scientists are trying to be creative in that. Subdivided, that is really no longer true because we know that there are particles inside of the atom and they can be stripped away from the atom. But in essence, atoms being the basic building blocks, if you do divide the atom or destroy the atom, it no longer is going to retain the properties that it once did. And we'll look at that new definition. But this is, somewhat true, still true, okay? Number 4, atoms of different elements combine in simple whole number ratios to form chemical compounds. And we mentioned this already. I keep using the compound of water, but they're going to combine in a certain ratio. 2 atoms of hydrogen to 1 atom of oxygen. That is always true. And in chemical reactions, atoms are combined, separated, or rearranged, and we're going to see this a lot. We're going to see lots of examples of this. So basically, during a chemical reaction, you have bonds that are broken apart, and then new bonds are formed, and as a result, something new is produced as compared to what was originally there. Okay? So this is definitely true. You need to know these 5 principles for Dalton's atomic theory. Okay. Inside of the atom, we are going to be looking at some of the subatomic particles. So atoms can be subdivided into smaller particles. All right? So along comes some other scientists to do some more work, and they build upon Dalton's ideas. All right? Not all, as I mentioned, not all aspects of Dalton's atomic theory were proven to be correct. Okay? So we now know that inside the atom we have other particles. We have just modified Dalton's theory just a little bit. Okay? So as I mentioned before, the important things about Dalton's theory are still correct. All matter is composed of atoms, and atoms of any one element differ in properties from atoms of other elements. Atoms are unique to that particular element. Okay? All right. Let's pause here for a second, and I would encourage you to take a second and answer these 3.1 review questions on your own and see if you can answer these, being able to test your knowledge in 3.1, and then come back and we'll dive into 3.2. All right, 3.2, we're going to look a little bit deeper into the atom, and we're going to, analyze it, pull it apart, and see what's inside the atom. And you're probably already familiar with this, so if this is a review, great. This will just build upon what you already have learned. So now, here's how the atom is defined. Atom is defined, and you must have this definition in your notes. It is defined as the smallest particle of an element that retains the chemical properties of that element. So for hydrogen or any other element, its atom is going to hold on to its properties. So what that means is an atom is going to react the same, one atom is going to react the same, one atom of hydrogen react the same as a billion atoms of hydrogen. Okay? So an atom is always going to maintain, retain, hold on to the properties of that particular element. The atom is composed of, we kind of divide it into 2 sections here. You have the very dense nucleus, kind of in the center of the atom, and then you've got around that, you've got the surrounding area. And inside the nucleus, you need to know that you've got your protons, which are positively charged, you've got your neutrons, which are neutral, and outside the nucleus, in the region, the cloud, sometimes they're called orbitals, as we'll talk about later, that region, that area, that's where your electrons, and those are negatively charged, that's where they reside. Okay? All right. Let's talk a little bit about these subatomic particles and give you some information, some characteristics about them. Okay? Now, let's look at a little bit of how some of these subatomic particles were discovered and some of the properties, how they were discovered. All right? We're going to look at 2 experiments in particular and why they're significant in the discovery of subatomic particles and their properties. So first one here, the scientist took what is called a cathode ray. This is a cathode ray tube. This tube right here is a vacuum. There's no air in there. And it's hooked up to a source of electrical charges, a source of electrons, if you will, a voltage source, a battery. Inside of this tube here, you've got these wires coming in and then connected to 2 plates. Here's a plate, and there's your battery right here. Well, what was discovered is that as the electrons build, as they would build up on the plate here, the pressure, if you will, the electrical pressure would be so great that they would start to stream across the other side and connect the circuit, complete the circuit, and would flow through this battery circuit. Okay, so you have a flow of electrons going from this plate here to this plate here, going through a vacuum. Okay, and some scientists took this setup, one in particular here, this English physicist, his name was Thomson, and this was way back in 1897. He was able to then place a magnet close to this cathode ray tube, and he noticed that the stream of electrons actually would bend. Okay? And so from that, he knew that the magnets had magnetic properties. Okay, you guys know that the magnet has a north and a south kind of pole to it, right? Well, this electrical charge had magnetic properties as well, and so it reacted to this magnet being in close proximity, and he found out from this experiment he could then calculate the ratio of the charge of the particles to the mass of the particles. He found that this ratio was the same no matter what metals were used in the cathode tube ray. So he was figuring out that, you know what, these particles are not unique to the metals that I'm using. They are in all metals, and those are the electrons that we were talking about. Okay? From this experiment, you don't really need to know exactly how he did the calculation or anything like that, but he was able to figure out the charge of an electron and the mass of an electron using this experiment. That's what you need to understand. You need to kind of understand how it was set up, that electrons are flowing through this tube here, and he held a magnet to it, and because the magnet caused the electron, the stream of electrons to bend a certain amount, he was able to calculate the charge and the mass of those electrons. Pretty phenomenal. Go way back in 1897, right? And so we're going to look at the mass and the charge of that electron in just a second. Okay? He also proposed kind of a model to explain what he was experimenting with, what he was finding out. And he came up with what is called the plum pudding model. And you need to know this and understand what we mean by that. His plum pudding model basically said this. We've got a nucleus. This is where your protons and neutrons are. And then around that nucleus, basically you've got a big bowl, if you will, the model, big bowl, big region, big area of just all these negatively charged particles. Okay? It's like a big bowl of negative charges, and he called that the plum pudding, as if this was a bowl of plum pudding. All right, plum pudding, you got your plum in the middle, and then all these negative charges all around. Okay? That's not exactly how it is, obviously. We're going to learn more about that, but you just need to understand his concept back then. The other experiment that we want you to understand, that I would like you to kind of conceive, or not conceive, but understand, is this idea of a thin gold film, or foil here, and what was discovered about the nucleus from this experiment. And I'm going to explain this a little bit. So again, two scientists are going to run this experiment, and here's what they did. I'll explain it. You need to be able to verbalize this maybe at some point, so make sure you understand it. They take this device here, which is a source of radioactive fast-moving particles. Okay, these are basically particles that are being emitted because the atom is being excited so much they're being emitted from the nucleus. So you've got a stream of tiny, tiny particles that are coming out of this box, and they point that at a very, very, very thin sheet of gold. Super thin. And around that then, they place this screen that is going to detect any of these particles that hit it. Here's what they discovered. They shoot the stream here, and some of the particles go straight through. And say they see that because there's glowing on the screen back here. They can tell when the particles hit the screen back there. They shoot and they go right through the gold foil. Every once in a while, a particle would hit the gold foil and ricochet, and they would detect it somewhere else on the screen. It would actually bounce off something. So you see all of these areas where these particles, these radioactive particles, are then either passing straight through or slightly ricocheting off of something in that thin gold foil. So here's what the scientists determined. They determined that something is in there that is causing these radioactive particles to bounce off and go a different direction. And that particle, whatever that is in the gold foil, must be very, very dense. So they determined that atoms have small, dense, positively charged core. We call that now the nucleus. Okay? This experiment was set up by Rutherford. So you need to know the Rutherford experiment, or the gold foil experiment. Okay? If you zoom in, this is basically what's happening. Here are the radioactive particles, and most of them pass straight through. Most of them pass straight through because the nucleus, believe it or not, is mostly space. That's amazing. Only a small part of the atom is dense matter called the nucleus. So every once in a while, these streams of these radioactive particles would bounce off, be ricocheting off of that nucleus. These are positively charged particles coming in, and so they determined that the nucleus must be positively charged as well. Okay? So, one experiment helped scientists understand a little bit more about the electron. The other experiment here helps us understand a little bit more about the positively charged nucleus where the protons are. So make sure you understand those two. So what you need to understand is, and it's all summed up here kind of nicely for you in this chart, is in the atom you've got an electron, you got electrons, and these are the symbols that are sometimes used for electron. We'll use this one predominantly. Okay, this other one here is showing you, the top number is showing you the mass, and the bottom number is showing you the charge, and the E is just what we use for the symbol for electron. Okay, its charge is 0. Its mass is so tiny we just say it's a 0. Okay, and these here are other quantities for the mass in what are called atomic mass units and kilogram. The proton is in the nucleus. Okay, you need to know the electron is found outside the nucleus in addition to its charge and mass. The proton symbol here, you put a P with a plus, or you can use this, because we used H here because hydrogen, if you take away its electron, is just a single proton. So again, here's its mass and its charge. Charge is 1, mass is 1. 1 atomic mass unit. A neutron, here's the symbols. Notice it has a mass of 1, but no charge. Charge is 0, mass is 1. And you need to know it's in the nucleus as well. Okay? All right. An incredible thing, though, this is phenomenal. If you miss this, this is gonna. I hope it's going to be astounding to you. Okay. Inside the nucleus, you've got all these positive protons, especially as the element increases in its mass. As you get larger and larger atoms, you're going to have more and more protons in the nucleus. Well, protons are all positively charged. You know that positive charges repel each other. They push each other away. Well, how in the world can we have all of these positive charges so tightly packed together in the nucleus? Scientists really don't know. We don't really know. All we know is that there must be some force in that nucleus holding all of these positive charges together, which is not what we would expect. So, particles that have the same electric charge usually repel each other. So we might expect that a nucleus with more than one proton would be unstable, but they're not. They're not unstable until they get hundreds of protons in there. Then you get radioactive material. Okay? Or I think maybe around 80. Maybe around 80, then you start to get some of the more unstable radioactive material. However, a force, we don't know what force, a force exists. There has to be a force there that is going to be holding two or more protons together in the nucleus that's going to overcome any electrical repelling force that's trying to push them apart. And scientists don't understand it exactly, so we just call this the nuclear force. Okay? This force occurs when two protons are very close to each other. Very close to each other. So, a similar force acts when two neutrons are very close together as well. Neutrons are neutrally charged, and that's going to hold the neutrons together. But in essence, what you need to understand is that this very mysterious nuclear force, it is a short-range proton to proton, or neutron to neutron, or maybe it's a proton to neutron force, but somehow something is gluing all of those forces together, those particles together in the nucleus, and that is referred to as the nuclear force. Okay. So this force these forces allow atoms with up to 83, as I mentioned, okay, around 80 positively charged protons in the same nucleus to be stable. If you get past 83, then it becomes unstable and you start having particles leaving the nucleus. That's radioactivity. Okay? All right. That's 3.2. Again, I would refer you to the review here, and I encourage you to answer these questions and make sure that you can, looking back at the interactive reader or from your knowledge from this video. All right. I'll see you in the next section here, 3.3. All right, ladies and gentlemen, in 3.3 we're going to talk about how we're going to bundle atoms so that we can count them very easily. All right, I'm going to try to make this as straightforward as possible. Now, let's look at some of the key points here. All atoms of an element must have the same number of protons, but not the same number of neutrons. We'll talk about these subatomic particles and why they're important. I think one of the most important things you have to understand is that for any element, the number of protons in its atoms never changes. Never changes. Okay? So if you look on the periodic table, here's an example. This is lithium. It is the third element on the periodic table. This 3 up here is telling you the number of protons. And that never changes for lithium. A lithium atom will always have 3 protons. Always, always, always. You must know that. You must know that an element's number of protons in the atom never changes. It is like its ID, its fingerprint. If you know that an atom has 3 protons, you know automatically it is lithium. Okay? Automatic. That is often referred to as its atomic number. Okay, like I said, an ID number. Okay? Now, the number of neutrons can change. That forms isotopes. We'll talk about that. The number of electrons can change. That forms ions. We'll talk about that. But for any element, its number of protons never changes. Okay? Never changes. If it does change, you've got something different. It's no longer the same element. Okay? All right. We'll talk more about the periodic table and the periodic law later on, but it suffices right now just to understand that this top number here is the atomic number. It tells you number of protons. Okay? I told you that the number of neutrons can change. If the number of neutrons of an element's atom changes, you create what are called isotopes. So for example, let's use hydrogen. Hydrogen has 1 proton. All hydrogen atoms have only 1 proton. But the number of neutrons might change. Okay? So, like many naturally occurring elements, hydrogen atoms can have different numbers of neutrons, not protons. So, those are called isotopes. 3 types of hydrogen atoms are known, 3 different isotopes. Okay, it doesn't mean that they all appear in nature the same abundance. Most of hydrogen, as we know it, is what is called protium. Okay, and then there's deuterium and tritium. Protium has 1 neutron. This has 2 neutrons. And this has 3. These isotopes, you need to have this definition in your notes. They are atoms of the same element that have different masses because they have different number of what? Neutrons. They have to have different number of neutrons. Okay? And it is the neutrons and the protons together that give an atom its mass. Okay? An isotope is identified by its name. You can give it a name, or you can just identify it by its mass number. The mass number of an isotope is the total number of protons and neutrons. Those are the two particles in an atom that give it its mass. Okay? So for example, let's go right here. Protium has 0 neutrons. I apologize. Okay, it has 0 neutrons. This has 1 neutron, deuterium, and this has 2 neutrons and 1 proton. Okay, so this here, let's just do this really quickly here. This has 1 proton, 0 neutrons. That's a 0 and an N there. So this mass would be a mass of 1. And you might see it written as hydrogen-1, hydrogen 1. Okay? This is hydrogen 2. Why? Because it has 1 proton and 1 neutron. Total mass of 2. This has 1 proton. It's always going to have 1 proton if it's hydrogen, but it has 2 neutrons. This has a mass of 3. So this is tritium, or hydrogen 3. Okay? So the mass of the particular element may change because the number of neutrons is changing, not because the number of protons is changing. You can fill in this table if you want to, but we just went through all of that a second ago. All right, as mentioned, we can use the hyphen notation, so we can write hydrogen 1 or hydrogen 2 or hydrogen 3 like this. Or we could use this other way to write the symbol. We could write hydrogen 1 as hydrogen. It would be 1 and 1. Okay. Hydrogen 2 would be 2 and 1. And hydrogen 3 would be 1 and 3. Okay. So this is a nuclear symbol. And what does it show? In the upper left of the element symbol indicates the mass. So this is the mass, 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 and the number to the lower left indicates the atomic number, the number of protons. So 1 proton, always 1 proton, always 1 proton. Okay? All right. And this basically, when we talk about a nuclide, the nuclide is basically a general term for the specific isotope of an element. So we're talking about different nuclides here. All right, it's not crucial. We usually refer to them as isotopes. You won't hear me say nuclide very much. Okay, so here are isotopes of hydrogen and helium. We should be able to fill in this table very quickly. You can do it with me. In fact, you can pause this and try to fill it in on your own and then come back and check. Hydrogen 1, or protium, here's the nuclear symbol. It has 1 proton, 1 electron. If it's a neutral atom, 1 electron, 0 neutrons. Hydrogen 2, deuterium. It has, here's a symbol, and that symbol tells us it has 1 proton, but the total mass is 2, so it must also have what? 1 neutron. It's always going to have 1 electron if it's neutral. Hydrogen 3, or tritium, has, here's the symbol, 1 proton always. Mass is 3, so it must have 2 protons, and it's always going to have 1 electron if it's neutral. Helium, let's talk about the element helium. Helium-3, here's the symbol for it. Bottom number tells us there are 2 protons. The mass is 3, so there must be 1 neutron. And electrons are always going to be the same as the number of protons in a neutral atom. Helium-4, here's the symbol. It tells us, bottom number tells us it has 2 protons. The top number tells us the mass is 4. Well, that must mean it has 2 neutrons. 2 plus 2 is 4. And it has the same number of electrons as protons to be neutral. Okay? All right. I'm just going to mention really quickly here the atomic mass. When we talk about the atomic mass unit, sometimes referred to with a U or AMU, and it is a relative mass. In other words, you're comparing the masses of everything to something else. One atomic mass unit is 1/12 of a carbon-12 atom. You don't need to know that specifically. You just need to know that the atomic mass unit is used to measure tiny, tiny, tiny atoms. And it is relative. In other words, it is related to a carbon-12 atom. 1/12 of the carbon-12 atom is 1 AMU. Okay? Now, what is that in grams? Well, 1 AMU is, look at this tiny number, 1.66, etc., times 10 to the negative 24 grams. It's incredibly tiny, just unbelievably tiny. Okay? All right. Now, not all of these isotopes occur in the same percentage, the same abundance. So, in our world, our atmosphere, we've got a lot of hydrogen-1 and very little of the other isotopes. So if you look here, in nature, 99.9% of all the hydrogen in the world is hydrogen-1. Only a small percentage is going to be hydrogen-2. So when we take a weighted average of that, you end up getting the mass of hydrogen. All the hydrogen isotopes in a sample are going to be, the average is going to be a little bit more than 1. Okay, because this mass here, this isotope has a mass of 1, but a little bit of hydrogen-2 is going to bump it up a little bit. The average, the weighted average. This is not just taking, 1 plus 2 and divided by 2. No, it's a weighted average. This isotope has a larger impact on the overall average mass. Okay, and that's true for all the elements. So you have carbon-12 and carbon-13. Look how much carbon-12 is in the world. 98%. That means the average, the weighted averages are going to be really close to 12, and has going to be a little impact from the 13. It's going to be maybe a little bit bigger than 12. We look here, look how much of the oxygen in the world is oxygen-16, and that's why the weighted average is really close to 16. Okay? And then you see here that these percentages are a little bit further apart, or not further apart, but a little bit, evenly spread. And so here 69% of all the copper is 63, 30% of all the copper is 65, and you can see then that pulls the average up a little bit above 63 because of the small abundance of the 65. Okay? So weighted average is just taking all the isotopes, but taking into account the one that you have, or the ones that you have in most abundance. Okay? This is how you would actually do the calculation. This is for copper. Okay, I'll show you really quickly here. So if 69.15% of all the copper is copper 63, and 30.85% of all the copper is copper 65, you would take 69.15% of that mass and get this number. You take 30.85% of the copper 65 mass. It's not exactly 65, as you can see, and get this number. And then you would add those two together to get the weighted average. That's how it's done. Okay? Now, how do we count these atoms? We have a mass. We can find the mass of these atoms, but how do we count them? We need to be able to count them up, okay, and be able to have some reasonable way to look at all of these and package them together. And that's where this idea of the mole comes in. Okay? So, the mole is kind of like counting a dozen eggs or a dozen donuts or something like that. The mole is nothing more than a number, but it is a number that is helpful for us to count the number of atoms, which are so small. So, like a dozen, you know that a dozen is 12. Well, a mole is just a number. A mole is a very large number. It is 6.023 times 10 to the 23rd. That's what a mole is. It's just a number. Okay? It's sometimes referred to as Avogadro's number because he's a scientist that is given credit for that. So Avogadro's number is the number of particles in exactly 1 mole. A quantity, it's just a quantity of pure substance. And it is given as 6.022, okay, I said 6.023, but 6.022 times 10 to the 23rd. Okay? So anytime I say a mole in science, in chemistry, we are referring to just a number, 6.022 times 10 to the 23rd. Just like when you say a dozen, you think of 12. Okay? Now, this number is astronomical. It's absolutely huge. But just think of it as a number, no more different than the number 12. We refer to it as dozen. This number is a mole. We need a huge number because even in a small quantity of something, some matter, there's a huge number of atoms in there. And there's no way we're going to count every individual atom. So we lump them all together in a package, in a pack, a group called a mole. Okay? We will be looking at the mole quite a bit later on, but it suffices to say it's a very important concept. The mass of 1 mole of atoms of a particular element is called the molar mass. So you need to have this written down. The mass of 1 mole of a substance is called the molar mass, the mass of 1 mole. Mass of 1 mole. Okay, so if you've got 6.022 times 10 to the 23rd particles of something, and you have the mass of that, that is the mass of 1 mole. That's its molar mass. Okay? We should be able to go from moles to mass and then to number of particles. And I'm going to show you how to do that right now. All right, I left you off here, ladies and gentlemen, talking about the mole. Sorry, I got interrupted here. And let's go back to the mole here and talk a little bit about how we do conversions from mass to moles and then to number of particles. Okay, very important concept. So we're going to slow it down here. If you need a break, take a break, walk away from it a little bit, get some exercise, and come back. But we need to really understand what we're going to talk about at this moment. All right? As I mentioned, a mole, 1 mole of anything, it doesn't matter what it is, anything. 1 mole is just a number. 1 mole is the quantity 6.022 times 10 to the 23rd, whatever that item is. In this case, we're talking about particles, atoms, compounds, ions, whatever. Okay? The molar mass is the mass in grams of 1 mole of whatever substance you were talking about. So, for example, carbon. If you had 6.022 times 10 to the 23rd carbon atoms, they would have a mass of 12.01 grams for 1 mole. For iron, 1 mole of this number of iron atoms has a mass of 55.84 grams. Okay? Copper, 63.55 grams for a mole of copper atoms. Now, where do we find this number? It's wonderful because it's on the periodic table. If we go back up here, I believe there was a right here. Okay? Here, for every element on the periodic table, this is your molar mass. It is the mass in grams of a mole of this particular element's atoms. So lithium's molar mass is 6.9 if we round it off to the nearest tenth. Okay? So let's come back here and let's learn how to do these calculations. We are going to go from mass to moles and then to the number of particles. Here's a little diagram to help you understand. If you are given the mass of a substance, okay, it's in a container, it's on your scale, it's whatever, you mass it and you figure out how much the mass is in grams, the mass of something. What you need to do is we want to convert that then to a number of moles, and then from there we can convert to the number of particles. In order to go from mass to number of particles, you have to go through moles. How do we do that? So to go from mass to number of moles, you are going to divide by the molar mass. That's what this is right here. You divide by molar mass. MM is molar mass. That would give you the number of moles. I'll show you the calculation in a second. Then if you know the number of moles, then you would multiply by Avogadro's number to get the number of particles in that number of moles. Multiply by what? 6.022 times 10 to the 23rd. Going back the other direction, if you know the number of particles, atoms, whatever, then you would divide by 6.022 times 10 to the 23rd. Okay? And likewise, if you know the number of moles, then you would multiply by the molar mass to get the mass. Let me show you a few calculations. Let me show you exactly what we're talking about here. If you are given a sample of aluminum, Al is aluminum, 11.9 grams, and you're told it's 11.9 grams, and we want to figure out what's the number of mass, what's the number of moles of that, and what are the number of aluminum atoms in that sample. Okay? So all we're going to do is we're going to look on the periodic table, find Al on the periodic table, and look underneath the symbol, and you will see the molar mass for aluminum. Let's find it. It's given to us here. The molar mass of aluminum is 26.98. So this right here, ladies and gentlemen, is the mass for 1 mole. Well, we obviously have more than 1 mole. Sorry, we have less than 1 mole because we have 11.9. We don't have 26.98 grams. We only have 11.9. So we have less than 1 mole. So you're going to take your 11.9 grams and you're going to divide by this molar mass. I'm going to show you the units, how they set up. 1 mole of aluminum has a mass of 26.98. I know I want to divide by the 26.98 because I want grams in the denominator to cancel the grams that I'm given. Okay? Grams are going to cancel. I'm dividing by the molar mass of aluminum. And then if I wanted to, it's not necessary in this problem. They're only asking for the number of moles. So if you took 11.9 divided by 26.98, you would get the number of moles right here, less than half a mole, 0.441. Okay, that means it's about half of 6.022 times 10 to the 23rd. And this is exactly what we would do to find the number of particles. If I want to actually find out how many particles, how many atoms of aluminum that is, then you would multiply by Avogadro's number, because 1 mole of anything is 6.022 times 10 to the 23rd, in this case, atoms of aluminum. Moles will cancel, and this is going to give you the number of atoms, whatever that number is. Okay? Think of it, don't forget, mole is just a number. It's like a dozen. If I say I want half a dozen, then you would take half times 12 to find out how many donuts that is. Same thing with moles. If you have 0.414 moles, you would just multiply by Avogadro's number to find out how many actual atoms that is. Okay? We can go the other direction as well. Actually, I'm going to find one here. Here's one where we actually are given the number of atoms. This is a good one. And you are asked to find the number of moles, and we'll also take it a step further and find the mass of that. This time, you are given, from our chart up here, you're given this. You need to go all the way to here, moles, and then here. Take 2 jumps to get to mass. So, here we go. You are given 1.20 times 10 to the 8 atoms. Well, remember, 1 mole is 6.022 times 10 to the 23rd. This number is a lot less than 6.022 times 10 to the 23rd. So we don't have a full mole. We only have part of a mole. Let's figure out what part of the mole we have here. We're going to take the number of atoms and we're going to divide by Avogadro's number, which is 6.022 times 10 to the 23rd. And that's what we're doing right here. Take the number of atoms that you're given, divide by Avogadro's number. You'll see that the atoms cancel. That's how many, that's a mole, 6.022. That should be a 0 there, 6.022. And when you do, you take this number, divide by Avogadro's number, you are going to get the number of moles. Just this first part of the calculation right there is going to give you the number of moles. Then, if you want to find the mass of that, for copper, a mole of copper, 1 mole of copper has a mass of 63.55. Again, on the periodic table, if you looked at copper, Cu, you would see 63.55, that number under the Cu symbol. That is the mass of 1 mole. So if this first calculation right here gives you the number of moles, then you multiply by the mass for each mole in order to get the total mass now of this number of particles. Okay? All right. I'm going to stop there. As always, I encourage you to look at these review problems in the handout and make sure you can answer all those. Check with me if you have questions. Check your answers, either with the ones that I supply, or maybe you want to talk to your classmates and work through it together and help each other out. Okay? Great job. Keep working hard. I'm always here to help. Reach out to me if you need assistance. Okay?